you generally would need an aggregate to do anything useful with a group by operator. A group by without an aggregate is essentially computing distinct. So you're creating one group for every distinct value of A, but you're not actually doing anything with the tuples that fall into that group.
So if you were to return something that didn't have an aggregate of the group by, you wouldn't get those groups right there? That's hash of groups.
Well,
A, right?
so if you were to not define an aggregate, you wouldn't get those groups. Yes, I mean in general, you wouldn't want to compute those groups when you're actually writing the code. When you're actually implementing the aggregate, you wouldn't actually want to store all of those groups up front. So just like in aggregation, you only need to see one tuple at any given point in time. You can you get 1, 1. That falls into the first group. You incorporate the 1, 1 into your aggregates, and you keep adding it. So you wouldn't actually need to store 1, 1, 1, 2, 1, 5, 1, 8. You just need to store after the first tuple, my sum is 1. After the second tuple, my sum is 3.
It was just a question out of curiosity. If you didn't have an aggregate, what would the output be?
A.
Just A.
Okay. Any other questions? Yeah. What would happen if B was a string? Yes, it would tell you that query wouldn't work. So no, SQL almost any SQL interpreter would alert you to the fact that B is not a legitimate input to sum.
And then when you did things like min and max, would fit in alphabetical order and sort by that?
Would min and max put things in alphabetical order and sort by that? I believe the spec doesn't allow you to do direct comparisons on strings. Individual implementations might try and do something sensible, but in general, aggregation on a string doesn't. There's no meaningful aggregate on a string other than concatenate all of these strings together. Question for you guys. How much space do I need in order to concatenate a set of strings together? Can I do it, so with sum or min max, I can store one integer. What's the amount of memory that I'd need to store for concatenating a bunch of strings? 2 strings, or, well, let's say I have n strings. Yeah. Exactly. So concatenation, although you can express it as an aggregate, is not what's called an algebraic aggregate, which means that you can't store it in a fixed amount of memory. You can't store your intermediate state in a fixed amount of memory. All right. Before I continue, any other questions on group by aggregates? All right. So today, like I said, what I want to talk about is storing data and how we actually work with different data representations. And pretty much everything that we're going to talk about today has to do with the memory hierarchy. So you may have heard this term before. It's basically this idea that any computer has multiple levels of memory, and each level of memory tends to make a speed versus size trade-off. The CPU has a set of registers which are really, really tiny, but they are really, really fast. On the other hand, you have virtual memory or hard disks that are on disks, really, really big, but also really, really slow. And all sorts of things in between. And when we try and put things and make, so basically what our goal is to make the best possible use of this, of the memory hierarchy as we can. So we want to figure out how to kind of effectively transfer data up and down this hierarchy. How do we And in order to do that, we need to know something about how the data is actually stored at different levels. In principle, we could copy large chunks of the data up and down, but we'd like to kind of have some ways to minimize the amount of data that we need to move up and down the memory hierarchy. Because every time we do one of those moves, that is usually where almost all of the cost ends up coming from in most, although not all, database computations. So to be a little more precise, today we're going to be talking about two components of a typical database engine. One called the buffer manager, which is responsible for optimizing transfer up and down the memory hierarchy and kind of timing things out. And one called the file manager, which actually handles the organization of the data on disk. So high level, what we want to do, anytime we need to do a computation, we'd like to use one of the fast representations of the fast levels of the memory hierarchy. And for the purposes of discussion, I'm going to treat RAM as being fast and hard disk as being slow. But if you want, you can treat pick any two levels and sub them in here. So we want to do computations on RAM, but in terms of actually storing the data and keeping it around for the long term, it's usually going to stay on disk. And in order to actually do a computation, you first have to read that data into memory, then you can actually do the computations, and then eventually we might need to write the data back. Now this read and write process is really expensive, and as I'll keep saying, this is basically where almost all of the bottlenecks in data management come in. So a lot of the time what we're going to use as a benchmark or as a measure of how much an operation is going to cost, we're going to use IOs, the number of read operations or the number of write operations that the computation needs to perform, because the CPU usually goes much faster than the disk. And that's only getting even more true now it's only getting even more true. Now, reasonable question, why don't we just stick with RAM? Why don't we just keep all of the data in memory and just be done with it? Short version, RAM is expensive. We don't necessarily want to keep everything in RAM because it's pricey, it's small, and what's worse, when you turn the machine off, the RAM goes away. Now that said, are these arguments convincing? Does anyone want to argue with me?
No.
No? Come on.
Well, they're not convincing, not that I don't argue.
Okay, they're not convincing. Good. So why aren't these arguments convincing?
The servers that are running the SQL database are going to have huge amounts of RAM.
Okay, so if you're Google, you have truckloads of money. Why don't I just spend all of that money on building out large server clusters with enormous amounts of RAM? Okay, fine. That still doesn't deal with the volatility issue.
There's many other architectures out there, like ZFS file structures that index the entire array and leave it in RAM. That's recoverable when you turn the computer back on.
Okay, so one possibility would be to keep all of the data in RAM, but just flush it to disk as quickly as possible. And actually, that's something that we'll talk about later on in the term. But the short version is, just because I put up a slide doesn't mean I necessarily agree entirely with it. Are in-memory databases viable? Yes. You can potentially build an entire database that lives entirely in RAM. But now, if you're dealing with an in-memory database, now you have essentially the same type of problem, except now you're dealing with RAM and the first level cache. So the first level cache is really, really tiny. The RAM might be huge compared to the first level cache, and you need to deal with exactly the same set of problems, just at a slightly different scale. So what we're talking about, I'm going to present this in the context of RAM versus hard disk, but there's the same set of arguments that I'm going to present for RAM and hard disk apply pretty much anywhere on the memory hierarchy. And there's also issues of persistence that we're going to talk about later on in the class, or later on in the term. Questions so far? Arguments? Okay. So, I'm presenting all of this so far kind of in the abstract. Let me make this a little more precise. So far we've been talking almost exclusively about asking questions. And one type, any type of question essentially boils down to a query. And if I am going to answer queries, here's basically a little bit of pseudocode that describes what I would do to answer one specific query. So for example, I might be reading from some relation, and I'd like to get back all of the tuples that satisfy some predicate. I have a selection operator on top of relation operator. So there's a couple of different bottlenecks that appear in this particular bit of, let me back up. This is kind of the naive way that I might implement that. So a while loop, and as long as I have more tuples to read out of my iterator or out of my source file, I read one tuple, and then I test my predicate, and I output my tuple. So far, fairly simple. But this ends up creating a couple of bottlenecks in perhaps a little bit of an unexpected way. So read tuple, if I'm actually going to disk and getting exactly one tuple off of disk, that's going to be slow because disks are slow. Disks have high latency. They may have reasonable bandwidth. Once you ask for something, they may be able to copy large chunks of data into memory, maybe not necessarily fast, but certainly reasonably fast. But every single request that you issue is going to cost you a bit of an upfront cost, bring with it an upfront cost. The other potential problem with this is that anytime you want to emit a tuple, you want to put a tuple either back onto disk or onto the display, or pretty much anywhere that isn't in the memory itself, that is also going to be slow. It takes a few seconds to update the display. It takes a few seconds to write things to disk. So both read tuple and output are going to end up being bottlenecks in this particular operation. So how might we potentially address these bottlenecks? Yeah.
Cache data that's being used often.
Cache data. Could you expand on that?
So if you have tuples that are being asked for a lot, make sure that those stay in memory.
Okay. So keep multiple tuples in memory. Or in the case of this, if we're only running it once, we could still read in a lot of tuples in one big go. If we're paying an upfront cost every time we go to disk, let's pay that upfront cost once and then just bulk load a large number of tuples. And yes, we do want to cache things as well. I will get to that in a few slides. So the short version is one way to optimize this would be to bulk load a large number of tuples and add a little bit of extra computation in order to first off, bulk load a bunch of tuples, and then a little bit of extra computation to actually handle the tuples themselves. So, right. So we're going to talk about a couple of different parts of back up. So we need to talk about a couple of different components in order to actually make this, this type of transformation possible. So first off, we need, in order to kind of bulk load data off of disk, we need some mechanism that will actually handle keeping track of what's in memory, what's not. And this component can also be used for caching. We also need some way of actually representing the tuples on disk. We need some way of encoding them. So we're today going to cover kind of this whole span of what happens with files. So in order to address this, we need to answer a couple of different questions. We need to know how the tuples are going to be represented on disk, how we're going to organize the tuples and group them together, and we need to understand what kind of metadata we need to keep around in order to be able to efficiently read data onto and off of disk, and then how to actually put this together and organize what you know at the moment, or what you have in memory at the moment. So a couple of terms before I begin. So we're going to talk about files, pages, and records. So file is a collection of pages, a page is a collection of records, and a record is going to be some sort of data value. And for our purposes, records and tuples are going to be the same thing. If I'm referring to a record, it's going to be a tuple on disk, and if I'm referring to a tuple, it's going to be a tuple in memory. So we need some sort of infrastructure that'll allow us to keep track of all of this, that'll allow us to keep track of what files we have, what data lives in what files, and how the pages themselves are organized. So let's start out by, let's approach this bottom up and start by discussing what goes into a record. So let me ask you guys, how would you represent a tuple on disk? And there's several different answers to this.
Comma-separated values.
Comma-separated values, okay. So we can take a tuple and we can store it as a set of fields, have each field separated by some sort of delimiter character, and then every single record gets delimited by another record, another delimiter character. CSV is the comma-separated values is the canonical case of this, where your field delimiters are commas and your record delimiter is a new line. All right, what's good about this? What's bad about this?
Easy to parse.
It's easy to parse. Okay, so I can read. Let me ask you, what do you mean by easy? Easy for the programmer, easy for the computer, easy for the human?
Probably the latter.
So it's easier for a human to parse. Yeah, so that's a really good advantage of some of these field delimited tuple formats, because I can just look at a CSV file and without squinting too hard, I can probably figure out how what data I have in there. Other advantages, disadvantages? So it's easy for the human. What about for the computer?
It's not as easy because it has to go through everything and find it.
Yep. So it's for a computer, as it's going through this this record, it needs to. It doesn't know where the second field starts, and if I wanted to read out, let's say, just the second and third fields, and I'd still have to go through almost the entire record in order to do that. What's worse, if I wanted to find just the fifth record, I'd actually have to go through the first four in order to figure out where the fifth record started before I even could start reading that out. What can I do about that? Well, let's hold off on finding the fifth record. What could I do to make it easier to find, let's say, the second field? Yeah.
They fixed that, so like an array, separate, but they can jump through it.
Okay, so I could Your example is an array. Yeah, so an array keeps every single field in a specific location. Now, the problem here is that we don't necessarily, the first field might be a short integer, the second field might be a 10-character string, the third field might be something different. But the cool thing is that in a database, you typically know what each field is, and you can usually assign a maximum size to each field. There's some exceptions, but in general, this will actually work. So what you can do is say the tuple starts at some location, and then I know how big my first field is, I know how big my second field is, so if I want to read out the third field, then I basically take the location of the start of the record, add the size of the two first attributes, and that's exactly where the third field starts. Now, this also means that we need to know what the layout of each record is. We need to know how big each field is. But we're typically going to be storing this usually in a component of the system that you'll sometimes hear referred to as a system catalog. And a system catalog is basically the list of all the create table statements that have been issued up to that point, among other things. All right, pros, cons. What's good, what's bad?
It's not very space efficient.
It's not very space efficient. Why would you say that?
If you're storing a string maximum length of 100 characters, if there's only one character in it, you're storing 99 blank characters.
Okay, so you've hit the nail on the head. If you're dealing with variable-sized records, you have to provision for the largest possible record that you could have. So if you're dealing with with strings that could be between 1 and 100 characters, then this ends up being less space efficient than a CSV file. On the other hand, there is actually some cases where this is more space efficient because you don't have delimiter characters. So if your record sizes are all fixed, this can actually be better. All right, other pros or cons? Yeah.
Might be hard for users to read because let's say L1, L2, L3, L4, take the max size of each character. If it's all numbers, we won't know where it ends, where it begins, and it's all full characters and stuff.
Okay, so if you want to represent integers as fixed size values, then you're going to have to encode this in a form that a human can't read. I mean, hex. Without your trusty hex editor, even with, it takes a lot more squinting to pull information out of a record stored in this format than it does to pull information out of a record stored in, let's say, a CSV format. Okay, so far we've identified kind of two approaches. One approach, comma-separated value, or field-delimited records, where you actually have to have a delimiter separating each field. And that means that in order to read the third record, let's say, you'd need to read the first two records, not records, fields. In order to read the third field, you'd need to read the first two fields as well. Now here, we've done away with that, but we've also prevented ourselves from using variable length records, at least prevented ourselves from using variable length records efficiently. Is there anything in between? Can we do something that is a little bit of both?
Probably.
Okay. Any suggestions for how we might be able to use variable length fields without using delimiters, or without using delimiters in the record itself? Store the locations somewhere else? Okay. Was that?
Yeah, I was just gonna say, like, whenever you have, like, store memory, how long the field is. That way you can have any field meaning during the application.
Okay. So rather than having every single field have one uniform length, why don't we just store the lengths as part of the record itself? So one potential way to do this would be to keep an array of offsets, let's say in some standard location, like the very start of each record, and then have that just point to the end of each field. So basically, we've just covered 3 different ways of laying out records on disk. For the purposes of the project, the first one is going to be what you're using for input, but in later parts of the project, you'll have to go back to disk, so you'll need to, well, you won't need to, but you might consider going to one of these as a way of making things a little more efficient. Any questions on record layouts? Yeah.
Which one is more effective or more widely used? Is it this one or the last one you used?
The question is, which one is more effective? So, I'm going to respond to this with a response that you should prepare for me to use throughout pretty much the rest of the class, and I'm going to say it depends. So the question is, I will ask you is, what are you trying to accomplish? And each of them has advantages and disadvantages. CSV is human readable, and it allows variable length records, but it also means that you need to, it makes the parsing a lot slower. The second layout works very nicely for fixed length records. In fact, it's probably the best way of representing fixed length records, but it's not human readable, or it usually isn't human readable, and it also, if you have any kind of variable length object in your record, or variable length field in your record, then it's wasteful. This, same thing, except in reverse. Probably the most efficient thing you can do without having fixed length records. Does that address your question? All right, so this is how you can store tuples in a, this is how you can store fields in a record. Now, the next question is how you can take records and lay them out in a page. Now this is going to be a little bit different because the page size isn't up to us. So a page, for those of you who remember your architecture class, a page is essentially the unit of input and output from a hard disk or a solid state drive or basically any kind of level in the memory hierarchy. You're going to transfer one unit of storage up and down the memory hierarchy in one go. And this is usually something like 2K or 4K, or in the case of something like the Hadoop file system, an entire megabyte of storage. So one page, we have to have some way of representing records in a page, but unlike records where we can control the size, here we just have this big chunk of memory that we get allocated, and we have to have some way of organizing data in those pages. Okay, let's take a simpler case and assume that all of our records are fixed size. So we're using the second representation. We know exactly how big each record is. What can we do? Okay, so we take the page size, we divide it by the record size, and that gives us that many slots that we can put records into. Okay, so here's a question. What if we don't have that many records? If we can fit 100 records onto a page, but we only have 60, what happens? You fill the rest with null. Or more generally, you need to have some way of indicating that the rest of those pages are not being used. And there's two ways of doing that. These are typically referred to as packed or unpacked. So in the packed format, you basically take all of the records, put them at the very beginning of the page, and then the rest of the records are free. And then in that case, you just need to store one number that tells you how many records you have. So which portion is packed and which portion is free. Which portion is full and which portion is free. The other format is unpacked. And there's a couple of different ways of representing this, but in effect, what you need in that case is 1 byte for every single one of those records, one additional bit, for each of those records that tells you whether it is being used or not. In the case, you could represent that bit as a null value, or you could represent that bit in some sort of bit vector that lives somewhere on the page. But you still need a binary yes/no. This record has something in it, this record doesn't. And that's going to be exactly 1 bit more of information than the minimum amount of space you need to store that record. All right, what are the advantages, disadvantages of each of these? Yeah?
For the packed format, you need to sort through all of your used and then gather them together and then have space at the very end. Well, not necessarily the end, but it's designated.
Okay, so for the packed format, there's a disadvantage in that anytime we delete something or anytime we remove something, we need to coalesce all of the records into this one. Is that what you were getting at? That you need to coalesce all of the records into this one chunk of the page. So anytime you make a change, well, you basically are performing potentially unnecessary memory copies. Okay, that's one disadvantage for packed. Yeah?
Disadvantage for unpacked is that you need that extra space to keep track of the repetition of the record.
Okay, so for the unpacked representation, we need space to keep track of every single record that is being used and not being used. Other advantages, disadvantages? So what about reading? If I'm just reading data, which of these do I want to be using? Packed. Why? Because it's all sequential. Sequential scans are a lot better than random scans. And for the unpacked format, I'll need to scan through the entire thing, whereas in the packed format, I only need to scan the records that I'm actually using. What about if I'm modifying something? What if I need to insert a record into the page? Which do I want to use? Unpacked? Packed? I hear some people saying, why unpacked?
Because you don't have to copy over all the data in the base. You can just insert it.
Okay, so if I'm inserting something, I don't need to do any copies. What's the argument for packed?
Packed wouldn't necessarily need to copy either, you just add n. It's not necessarily a sorted packed list.
Okay, so it depends on how the data is actually laid out. If I care about the order, I'd need to do some copies. If I don't care about the order, then in a packed representation, I just tack it onto the end and I'm done. What about an unpacked? How would I do an insertion? If let's say I didn't care about order, how would I do an insertion into unpacked? Yeah.
Would you iterate through until you find the first empty?
Exactly. I'd iterate through, find the first empty record. So insertion all of a sudden becomes an order n operation. So again, which of the
But you have the bit representation.
Well, it's still in. So you do have the bit representation, but you have to iterate through the bit vector. So you're still doing n comparisons. Granted, you could do something clever like compare the first 2 bytes of that and see if you have any free space in the first 2 bytes. You might be able to get that search done in logarithmic time, but it still ends up. If you don't care about the order, it's still log n versus constant. So both these representations have their advantages, they have their disadvantages, and which you'd want to use, again, depends entirely on what you're trying to do, how you're trying to store the data, and what types of changes you anticipate happening to the data. Like I said, if you're doing read-only, then packed just packed and done with it. But if you're doing any kind of update operations, there's advantages and disadvantages to both. Okay, so we've covered half of the space here. This is what we can do if we know the size of the record, if we're dealing with fixed size records. What if we're dealing with variable sized records? So this, not necessarily CSV files, but let's say we're dealing with that last data representation, where we know we store the length as part of the record. What can we do? So are these going to work in that case? Can I use one of these representations for a variable length record? Okay, so I could potentially use something like packed, but would I be able to, would I know where record 2 starts? No. So I need to have some way of scanning through the entire record. Now I could use something like CSV, which is essentially what you're describing. I use a packed record. I just pack everything at the start, and then I need to scan through, find the first record delimiter, and that's where the second record starts. Then find the second record delimiter, that's where the third record starts, and so forth. So if I wanted to find the 15th record, I'd have to scan through 15 records to find it. If I wanted the 100th record, I'd have to scan through the first 100 records to find it. Can I do better?
Always.
Always. Okay. How?
Ask me how.
Okay. Damn it. This is my secret plan. Have you teach the class. Okay, so what did we do when we had variable length records and we were trying to solve this problem? We indexed them. We built in a little bit of extra information that we could use in order to locate each of the records. And we put all of that in a clearly marked, clearly identifiable place. Now, this is a little bit more tricky with pages because you have to have all of those markers. You have kind of your chunk of data that you're using for your records, and you have a chunk of data that you're using for the locations. And because because of the fact that the page is fixed size, because you can't allocate a page specifically for a set of records, you kind of want to put these on opposite ends of the page. So usually what will happen is, so one variable sized record format that works is where you put your list of pages at the, list of records at the end of the page, including a pointer to the last record and where the free space starts. And then you have the first n bytes of the record, of the page, however many that is, to actually store the records. What are pros and cons of this approach? Yeah.
Human readability is a problem.
Okay, so your records are going to be scattered all over the page. So even if it was in some sort of string representation, a human wouldn't necessarily wouldn't have an easy time figuring out what was a record and what was garbage data.
Is that really a disadvantage? It's not like you're going to be looking at this directly, right?
Not necessarily. It is a disadvantage. Whether it's a disadvantage that's meaningful depends on how it's being used. I mean, each of these representations have trade-offs. There's pros, there's cons, and your goal is basically to figure out which pros are important and which cons are not important. Yep.
You could have a page fault, but otherwise you could just have a bunch of blank space at the end.
So you could have a bunch of blank space at the end. You mean just wasted space?
Yeah, so like if you are in a document where your record goes past the amount of size of the page, then you have to store the rest of it on another page.
Okay, so you have this list of pointers, and you have this set of variable-sized records, and you might end up with a little bit of wasted space after the last record. And when you get a new record, you may not be able to fit it in there, so you may need to put it onto another page. So this is potentially wasteful because you don't necessarily have the ability. Excuse me. You don't necessarily have the ability to control how much space every record takes up. Knapsack problem is NP. So don't even trying to optimize this is possible, but will be slow. Okay. So there's potentially some wasted space in this representation compared to the packed CSV style. Any other pros, cons? What happens when we delete a record?
You don't have to move anything else around. You just want to do that record.
Okay, so you don't actually need to delete the record from the page. You just need to delete the pointer. So that's a pro. Deletion is fast. Is there a con associated with that as well? Yeah, so that chunk of memory is now wasted. I could potentially identify that that chunk of memory wasn't being used, but then I'd still not be guaranteed that if I get a new record that it would fit in there. So with this particular type of format, periodically you're going to want to go through and compact the records back down, eliminate all of this wasted space by essentially rebuilding the page from scratch. Okay, so we have a couple of different ways of laying out records in a page. We have a couple of different ways of success. Okay, so we have a couple of different ways of laying out records in a page and a couple of different ways of laying out fields in a record. Now, the last thing that I suggest, that the last layer here is files. So a file, as far as the database or as far as the operating system is concerned, is basically a collection of pages. Usually a collection of sequential pages, but for our purposes, it's just going to be one big set of pages. And we have to be able to read a record, insert, update, delete a record, and scan a record. Now, there's a couple of different types of file representations. We'll talk about a few more of them next class. Today, we're going to focus on a really, really simple type of file called an unordered, or sometimes referred to as a heap file. I use heap in parentheses here because this has nothing to do with the heap data structure. This is just a file of unordered records. We don't care about the order of the records. We don't care about the order of the data. And we do care about the size of the file. So the new records may be added to the file. Records may be deleted. But we basically want to do a couple of things in order to maintain this file. So we need a list of pages, and we need, in general, a file system will allow us to allocate new pages, but it won't allow us to delete pages. We can make a file bigger, but we can't make a file smaller. So while we do want some way of allocating and freeing individual pages in the file, we have to handle that ourselves because the operating system generally won't do it for us, at least not necessarily efficiently. So let's say we have this list of pages. What can we do? We have some pages that that have stuff on them, and some pages that don't have stuff on them. How can we keep track of what's what? I just confused everyone. Okay, let's present this slightly differently. So a file is a collection of pages, and the operating system lets us take as many pages as we like. But every time we delete records, we might end up releasing all of the information on a particular page. So let's say I start off with a nice file. It's nice and full. I allocate a bunch of pages for it. So I allocate, what do we have, 5 pages. But over time, my data grows and shrinks. New values get inserted, new values, old values get deleted. And for whatever reason, I decide that this page, that I can shrink the file to a size of 5 pages rather than, 4 pages rather than 5. So I delete all of the data. Let's say this page has 2 records left on it. I realize I can move those 2 pages to my last page, those 2 records to my last page. Now I've got this really unsightly, empty page sitting in the middle of my file. Now, remember that every single operation, every single copy from disk to memory happens at the granularity of a page. So if I wanted to do a full scan of all of the records in here, I'd have to read this page, this page, this page, and that page. So if I wanted to do a full scan of all of the data, that would cost me 4 operations. But I've got this nasty, or it should cost me 4 operations. But I've got this nasty little empty page sitting here.
You said you can't read pages, you have to keep it around?
I have to keep it around because as far as the operating system is concerned, this is one long, long record. One long string of bits.
You just move it to the end?
You can't move it. Well, in order to move it, you'd have to take,
Copy the last page.
you have to copy all of this in there. And that's going to, that potentially can be slow. Okay, so I could put some kind of a flag that says, this guy has nothing in it. All right, great. How do I represent that? Do I store it? So I could potentially store it here, but that'd be kind of silly because in order to read the flag, I'd actually need to read the whole page in, and I've kind of wasted the effort. So what could I do? How do I represent that flag?
1 or 0 in the first section of the page.
All right, why don't I keep around a little bit of metadata in some sort of head page that tells me which of the pages in my file are actually present. So I could do this as a bit vector. Turns out with pages, there's actually another clever trick that you can play, at least with heap files. So with heap files, I don't actually have an order on the data. Because there's no order, the only thing that I can actually reasonably expect the system to do with one of these files is scan through the entire thing. So all I'll ever want to do is read in all of the pages. Any thoughts on what I could do with that? So what's a good data structure for representing stuff that I only ever need to traverse in order? Linked list. So what I could potentially do is on each page have a pointer to the next page that actually has information. I read one page in, and I just scan over the pages that way. And the other way would be exactly the same thing that we mentioned earlier, which is to have a directory page at the very beginning, which tells us which pages actually have stuff on them. So the advantages of each of these, the big, so comparing these two, why would we want to use one or the other? Yeah.
For the linked list one, now you have a linked list of 4,
Mhm.
and then let's say you fill up the 4 and you add more data. Does that mean you've got a fresh new page, or can you try to use the one that?
Oh, you can reuse the old pages. So you have one linked list going to the full records, one linked list going to the empty records, and you just pull something off of top, something off of one of the empty pages, and pack it up. Yeah.
Page lookup time,
Page loading time would be the only difference. Can you expand on that?
Lookup time, so like, it would be linear lookup for a necklace, and then it would be constant time for like page table.
Okay, so if I wanted to, linear versus constant time for a directory.
So you look for a specific page.
Okay, so if you're looking for a specific page. Yeah, so in general, if you have any kind of order or any kind of information about what tuples are where, then you'd almost always want to use a directory page rather than a linked list. In the case of a heap file, where any tuple, any specific tuple that we're looking for could be here, 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 here. If we don't actually know anything about the organization of those pages, then the linked list is actually still going to perform a little bit worse in terms of loading times, because you have to first read this page in, and you can't start this read until this page has already arrived in memory. So in general, the directory page representation is going to be a little bit better, although it requires you to keep more information in memory about which pages are available. The directory ends up being somewhat bigger as compared to the linked list. Yeah?
So there would be no speed disadvantage for the directory versus the linked list.
There's no speed. Would there be a speed disadvantage for the directory versus the linked list? So the directory could actually do better, a little bit better, because file systems typically tend to read things faster if you put read requests in sequential order. So if the directory page could tell me that both of these pages were necessary, I could actually read both of them out in one operation. That one operation would be a bit slower than just reading one page out, but it would be faster than reading them out one at a time. And it might actually make sense to go to the file system and say, just give me the entire thing. That might actually be faster than 2 separate requests, one for this chunk, one for this chunk. You could do that optimization with a directory page. You couldn't do that with a linked list. But on the other hand, a directory page requires you to keep a bitmap for every single page. And for really, really large data sets, that might end up being fairly large. So usually what happens is some combination of the two. You will end up with a directory tree that has a linked list of its own. All right. Let's see here.
So just to clarify, if you have a directory page and I'm searching for one record, I will potentially end up pulling all the pages at once and then scan them, not take the first page, didn't find the record I was looking for, go back to the directory, find the second page, go to the second page, search it, not find it, go back.
You just go to the directory, go to that, and find the designation of what I'm just go to that page.
Okay, so both of you presented a one approach. My answer is going to be a little bit in between. So the directory page won't tell you which tuple a particular. The directory page in a heap file. I'm going to stress that in a heap file, the directory page won't tell you or won't give you any information about which page a particular tuple lives on. So you can't just go to the one page. On the other hand, with a directory page, in principle, you could load this, check it for tuples, then load this, check it for tuples. Although, usually what will be faster is if you start loading all of them in, and as this page comes in, check it for tuples. As this page comes in, check it for tuples, and repeat the process, and then cancel any outstanding requests once you actually find it. But that's a good observation, by the way, because we'll talk about that next class, or sometime next week we'll talk about how you can actually do even better than this, if you know something about the data. Yeah?
So you're saying that the slow part is they use to load in the entire page, and then once you get to the bottom, you see the location of the next page?
So
Is that what you
the page, the basic operation that a hard disk gives you is give me a page, or give me a set of pages. And if I was doing this as a linked list, I could load this page in. In order to recognize that this was the second element of the linked list, I need to be able to read the last record of, or the part of this page.
So then, could you just like backload the page so that like you fill it from reverse, so at the very beginning of the page?
Can you bulk load? Basically, again, the operation that the disk gives you is load the entire page in. It's not load a couple of bytes in. Don't stream the bytes in. It's just load the entire page. So it's the page is either not there or in memory. There's nothing in between. I mean, there could be, but at least the way most hard drives work, it's either there or not. Okay. All right. So let's quickly. Okay. So we've talked about data representation. We've talked about how to encode fields into a record, how to encode records onto a page, and how to group pages together into a file. Now let's go back to what we started with and look at this idea of batching or caching, or basically how do we deal with the fact that the data is stored on these pages. The pages are typically stored on disk, but we don't necessarily want, we want to be able to load these pages into memory. We want to make sure that once we have something in memory, it can stay in there and be reused. And the component of a typical database system that handles this is typically referred to as the buffer manager. So the buffer manager is basically part of a typical database that has the ability to allocate pages, deallocate pages, and the ability to load pages into and out of memory. So from the perspective of higher levels of the database, the buffer manager basically keeps track of the available memory. Whenever you want to read from a particular page on disk, the higher levels of the database say, I want to read from this particular page on disk, and the buffer manager is going to make sure that that page of data is loaded into memory before the database can actually use it. There's going to be a whole bunch of chunks of memory that aren't actively being used. These are often referred to as free frames. So the buffer manager is basically going to keep this big array of frames, and it's going to load pages into these frames. Now, the database needs to be able to tell the buffer manager when it's actually using part of memory. And it's going to do this by means of a kind of locking mechanism called pinning. So the higher levels of the database typically tell the buffer manager to pin a particular page in memory. Say pin this page in memory, and this basically forces the buffer manager to keep that particular page in memory. Once the caller is done, then they unpin the page, although that doesn't force the buffer manager to release that page. It doesn't force the buffer manager to actually make that frame available for other pages. Instead, what will happen is that the buffer manager is just going to keep that page sitting in memory, and if it runs out of memory, it's going to release that page. If it still has memory later on, it'll keep it in. It'll keep the page in memory. And then, if that page ever gets pinned again, then if it's already in memory, great. If you run out of memory, you're going to have to. The buffer manager has to go back to disk and push things out. If the pages have been changed, it needs to flush the changes to disk, and it needs to have some way of picking among the pages that it has in memory what to throw out. So, I mean, there's tons of work on this. I'm sure everyone has encountered least recently used, most recently used, clock scheduling. Which of these policies you use can have a big impact on the effectiveness of the buffer manager, but I mean, basically, you have this chunk of memory. You have to decide how it gets used. So this might seem very suspiciously familiar. Has anyone encountered something kind of like a buffer manager? Operating systems? What part of an operating system? Virtual memory. This, what is this? Why do database folks have their own virtual memory scheme? The short version is this is basically virtual memory, and buffer managers and virtual memory kind of co-evolved together. At a really, really, really high level, they're the same thing. They're meant to keep things on disk and to page things into memory on an as-needed basis. But kind of the one example and the one compelling reason that I've heard so far to actually have a separate buffer manager in a database system is that operating system paging has to make a lot of guesses. So in an operating system, let's say that I'd like to read out enterprise officers that I know, I absolutely am absolutely certain that the enterprise officers are only going to be on the 3rd, 4th, and 5th pages of my file. So what will happen is that the database is going to issue a read operation for that first page. It's going to get loaded into memory over time. Then the database operation is going to issue a read operation for the next page. It's going to load into memory. Now, at this point, the operating system is very used to these kinds of access patterns. It's going to say, great, amazing, they're doing a sequential read. I love these things. I can just load everything into memory. Perfect. And so it's going to load the rest of the file into memory, or it's going to start loading the rest of the file into memory. Of course, the database only needs to read one more page in, so it's wasted time because you haven't gotten to this sequential read yet. And, it's wasted time because it can't necessarily realize that you're doing a sequential read until you actually start reading a couple of pages in sequence. And then at the very end, it'll potentially read in too much because it doesn't know where you're going to stop. Now, in a database, what can happen is that the database recognizes that it only needs a specific set of pages. So it makes sense for the database to potentially re-implement a buffer manager because the database can specifically read things. It knows what it needs to read. Now, this is something that you do in a really high-end database. If you want to squeeze every ounce of performance out of the database system, it makes a lot of sense to do this. Again, the database knows exactly what it wants to read in, and so it can be a lot more intelligent about optimizing the read process as compared to an operating system, which has to make do with a lot of guesswork. But quite frankly, at this point, virtual memory has gotten to the point where it's pretty smart. And unless you're building this super high performance database like Oracle or DB2, this is a lot of coding effort for not a huge amount of gain. So while I want you to be aware that buffer managers are a thing, they're an important part of extracting every last bit of performance out of your disk. At least for the purposes of building, say, 70–80% of the database systems out there, virtual memory is probably enough. Okay, so that said, any questions on stuff we've covered so far today? All right. We have about 4 minutes. I have a little bit of... All right, so I'm not going to go into this in depth, but there's one last bit of layout that I want you to think about. We'll get back to it later on in the class. I was kind of hoping to get it into this lecture, but right. So far, we've been working with this assumption that the record is the main unit of computation. But there are some cases where records can be really, 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 really big. And I think these numbers are actually a little bit on the low side. But there's, as a simple example, advertising data, such as you might encounter at Google, Facebook, Amazon, Bloomberg, blah, blah, blah. The data that they get out of log files and customer information can have hundreds or thousands or I think tens of thousands isn't entirely unexpected either. So if I wanted to store all of this, I'd basically end up with, well, maybe, what would I want in here? I'd want like a ID for the visit event, maybe the visitor's IP address. Maybe I want, some statistical information about the visitor. Maybe I can infer their age, their gender. Maybe some information about where they're located, region, country, city, zip code, even more detail. Maybe I have some information about their personal likes. So, I like cats. You end up very easily filling up hundreds, thousands, or even tens of thousands of individual columns. And let's say that I'd like to run a query for people who like both cats and spring break for, the trip to, there's this like hotels in Japan that give you like rooms with cats in them. So maybe I want to advertise that. Well, I'd like to find everything that just has these two Boolean values set. And for tens of thousands of columns per record, this is going to be incredibly, incredibly slow. Incredibly slow. So as a random question that I'll bring up again at the start of next class, how might I improve on this? So talk amongst yourselves after class. You can get out 3 minutes early, so plenty of time to talk. And how would we do this better? Does everyone see everyone on Tuesday? Yes. Yes. It will be on the resources page. Jim should upload them either in the next couple of days. Blame me for this. He got back to me with his office hours a few days ago. June is 3:30 to 4:30 on Tuesdays and Thursdays. It's now, as of this morning, it is posted on the website.
website.